Hello Internet, my name is Quentin and this is Blondihacks. I'm going to do a video today that I've had a number of requests for. This is a beginner's guide to surface plate work. If you're a regular viewer, you know I love traditional layout and the surface plate in particular. And you might be wondering, why do I use it? And maybe you're interested, so let's find out right now. This is a beginner video, so I'm not going to assume you know anything about surface plate or traditional layout. This, of course, is my surface plate. You've seen it lots on my channel, and it is nothing more than a big old rock that's been ground extremely flat. Now, why would you want to use a surface plate? The short answer is if you've ever found yourself doing this with your calipers, you should have and use a surface plate. Now, look, we've all done that with our calipers, and I think we all know you're really not supposed to do that for a number of reasons. Of course, it's not really good for the calipers to do that because you're putting some stresses on them in directions they aren't really designed for. You're also potentially wearing out the tips. I mean, they are stainless and generally hard, but they are not scribing tips and they're not really designed for that. So if you do a lot of that, you will eventually wear the tips out on them. And there's an accuracy cost for doing that because, of course, the jaws are the same length. So when you're scribing like that, the jaws are at an angle, and so you're introducing cosine error. You can't get the jaws perfectly flat. That said, there are dedicated scribing calipers that you can't buy. They have one jaw longer than the other, and they have a carbide tip on them designed for scribing. So if all you really want to do is the occasional one of these, it is occasionally helpful, but if you want to do a lot of that, you can buy scribing calipers. However, the surface plate is a more accurate, more reliable, and more fun way to do this job and many other jobs. Conceptually, you can think of the surface plate as a perfect flat plane. Of course, it isn't actually. Physics laughs at all such theoretical notions, but you can treat it that way. It's sufficiently perfectly flat that you can treat it that way and use it as kind of the universal reference for all features on all parts at all times. It's like having a single source of truth for the entire universe right here in your shop. Step one then is to acquire yourself a surface plate. These are pretty easy to get. This is a really good size, I think, for a model engineer. It fits on the end of my bench, doesn't take up a lot of space, and if you watch my channel, you've seen that it's big enough for everything that I do here. If you've seen me put my entire locomotive on this thing to take absolute measurements on all different parts of the locomotive to compare them to various standards. This one is 12 inches by 9 inches. It's kind of a standard small to medium size for a home gamer. And like I said, I think it's a great size. There's lots of reasons you don't want one bigger than that. One of those is shipping. So I bought this guy from Little Machine Shop, and I bought it when I was living close to their warehouse, and so I could drive over and pick it up. Don't underestimate how heavy these things are. It's a solid piece of granite. So I'm not sure what the shipping on this would be if you had to ship it across the country or internationally even, but it's going to be expensive because of how insanely heavy these are. In fact, it's probably over the weight limit for like UPS and some of the standard couriers. So they are heavy. So that means you pretty much want to get one locally. If you can't, then what do? Well, there are other options. A really common old school model engineer trick is to go to a granite countertop supplier and ask them for an offcut. Believe it or not, regular granite countertops for kitchens are actually ground to an extremely good standard of flatness. And for the kind of work that you're doing in a hobby shop, they are plenty good enough, and you really don't need a lot more than that. Of course, they're not as thick as a kind of real surface plate, but again, they don't need to be. The thickness of the plate is lending you some additional thermal stability because in principle, of course, this being a stone, it will shift and move a little bit with temperature changes, and the thicker it is, the more massive it is, the less of an effect that has on it, the more thermally stable it is. But again, for the kind of work that you're doing and the work that I'm doing, that really doesn't matter all that much. Any kind of reasonably flat surface is going to be good. And by reasonably flat, I mean something that has been ground. So Blanchard ground like a granite countertop, or something like a lot of model engineers in the past have used pieces of glass. If you can get a good piece of picture frame glass that's reasonably thick, that can also work. But let's also talk about what you don't need. This is one of those areas where enthusiastic, prosumer-minded beginners get very excited and will run out and buy a 6-foot pink granite Starrett AAA surface plate mounted on 3 points on a fluid-filled bench, and goodness, you don't need to do that. Unless your name rhymes with Blenzetti, there is nothing that you will do in your home shop that could ever even approach needing that level of quality. Now, there's no wrong way to hobby. If spending $5 on a surface plate setup makes you happy and you enjoy it, then go for it. But I don't want you to think that you need to do that or that it's going to make you a better machinist in some way. The flatness of surface plates is measured with a letter grade system, and this is a B grade surface plate, so kind of the lowest grade, a workshop grade as they call it, not something you would find in a precision inspection area in a scientific, machine shop, something like that. But again, this is just a simple, cheapo B grade plate. I think this cost me $30, is absolutely more than good enough for anything that you are ever going to do in a home shop. Let's talk care and feeding now of your surface plate. It's funny, often those same people that have the $5,000 AAA Starrett surface plate also store all their tools on it. And yeah, don't do that. Take care of it. Even a cheap one like this, it will wear out, and you don't want to be putting divots and scratches in it. So keep it clean, because things sitting on the surface over time, dust and so on, will abrade the surface and wear it out. And as you've seen, I keep mine covered when I'm not using it. This is just the shipping crate that it came in when I picked it up at the warehouse. And I mean, look at how dirty the top of it is. This is all stuff that's not on my surface plate. But yeah, keep it clean and don't store tools on it. Don't use it as a lapping plate. Don't use it as a cutting surface for your decals, or, just don't do anything except surface plate work on it, and keep it covered when you're not using it. For the same reason, get in the habit of keeping it clean. Give it a wipe every time you use it, and anything that you set on the plate should have its bottom wiped clean. And that's for multiple reasons. Obviously, it's for accuracy. Any debris or anything, a chip or something that's sitting between your instrument or your part and the plate, is going to interfere with your readings. But also any dust or anything that's sitting between those surfaces is going to grind. And surface plate work is all about sliding things around, and you don't want to be sliding things around when there's grip between them. So everything stays clean, and if you do all of that, your surface plate will outlive you. This surface plate's almost 10 years old, and there's not a mark on it. It's as good as the day I bought it, and it's just because I take the very basic precautions to take care of it. Well, this is all fine and good, but what use is a surface plate aside from basic scribing, like I alluded to earlier? Why would anyone use it in this day and age? Because nobody does use it in a modern production shop, right? You don't see surface plates in use anymore in real shops. And so you might ask yourself, why? Well, the methods that I'm going to be showing have largely been supplanted by newer tools. Obviously, in a CNC world, it's kind of lost its relevance, and it's also largely supplanted by digital readouts. If you have a DRO on your milling machine, you probably can get away with never using a surface plate. You don't really need to do layout as much as you might have had to do in the before times. However, there is still lots of reasons to do it, as I'll show, and it's also just fun, and it also teaches you a lot about the fundamentals of precision. There's a lot of value in learning traditional methods, even if you're not going to use them, or even if you don't understand why you might want to learn them, because things are traditional generally for a reason in technical fields. If people have been doing something this way for 100 years, such as surface plate work, there's probably good reasons for that. And you may not understand those reasons at first, but by learning those methods, you will come to appreciate subtleties about precision, for example, that you might not have otherwise. The world is full of smart people, and the world has always been full of smart people, and the people that came before you have figured out a lot of things. So it behooves us all to learn why they did things that way before rejecting those ideas, which is not to say everything old is automatically better. People also did lots of superstitious and nonsense things in the old days that we don't do anymore. But surface plate work has a lot of valuable lessons in it. So, learn about the past and take it with a grain of salt and compare it to what we do today. Let's get into usage now. The fundamental tool of surface plate work is the height gauge. This, of course, is a relatively fancy modern one. Traditionally, a height gauge was literally just a precision ground flat block with a pointer on it sticking out sideways. And the height of that pointer would be set with a gauge block stack. That was, of course, very accurate and was possible with the type of manufacturing that they had at the time. Nowadays, of course, we have fancier ones. This is an analog clockwork one. I like tools without batteries in them, but of course you can also get modern digital ones as well, and they have some advantages. For example, the ability to zero a height gauge anywhere along its travel is frequently useful in surface plate work. It will save you some of the arithmetic that you'll see me doing with the analog one, but like I said, I like working without batteries because the nice thing about this is the batteries are never dead. Now we call it a height gauge, of course, because all it's doing is measuring the height off the surface of the surface plate. And that sounds like a trivial thing, but that is actually an incredibly powerful tool. So you're going to want to zero your height gauge. When it's all the way down, you of course should be reading 0 on it. If you're not, check it to see if there's any debris on the underside of the pointer or underneath it on the plate. And you shouldn't be pushing down on it too hard, just kind of move it down until it's touching nicely, and it should zero out like that. And from here on, I know I can move up any distance, and the underside of the tip of that pointer right there is going to be at that exact measurement. And that's important because this thing is not just a flat surface, this is a carbide scribe. And the corners of this thing are very accurate, and the bottom surface of it has been precision ground and lapped. So the corners of this thing will scribe perfectly at that height, and the bottom surface of it is perfectly measuring distances above that surface plate. And those two things are the secret to all of the things that you can do with a surface plate. This tip is also replaceable, as you can see. I can just loosen this thumb wheel, pull this whole thing out, and buy a new one if I need to. If you chip this thing or otherwise damage it, of course, it ceases to be of any value. So it's worth taking care of your height gauge as well. Don't put it anywhere where it's going to get knocked around or damaged. You're also going to need reference blocks of various kinds, so especially squares. So you'll see me use a 1, 2, 3 block a lot as a square reference. These things are generally very square, sufficient for what we're doing. You'll also see me use a precision square at various times, and also V blocks are also very useful on the surface plate. These are all useful for references and also for holding specific shapes of parts and holding them in specific orientations. Surface plate work can be broken down into 2 basic categories: inspection and layout. The inspection side of it is pretty self-evident. You can place things on the surface plate and use the height gauge to measure how high they are. You can measure the centers of holes by using gauge pins in those holes. You find the top surface of the gauge pin with the height gauge, subtract the radius of that pin, and you found the center of a hole. So this can be used for measuring distances on parts, seeing if you've hit a dimension on a part, checking how far something is if you're making a matching part, all those types of jobs. Just about anything that you might do with other forms of metrology can be done on a surface plate. The second category, layout, is what you see me doing mostly, and it's the part that is a lot of fun and can save your calipers at the same time. The way to think about layout on the surface plate is that it's just like doing it on your bench with scribes and illegal use of calipers, but everything is vertical because, of course, the height gauge moves up and down and scribes horizontally. So that's where your squares and such come in. So to scribe that line that you saw me scribing earlier on the bench in the antisocial way, I would do that same thing here on the surface plate by putting that piece of brass up against a square reference, then setting my height gauge to the distance from that edge that I was scribing with the caliper. And then I lock the height gauge so that it doesn't move while I'm scribing, and then strike my line. Just like that. So you can see it creates a much nicer line, and it's more accurate because there's no cosine error created by the tilting and the arbitrariness of how you're holding the caliper. There's a lot of angles involved in how your hand is holding the caliper, and there's some unavoidable angle involved in order to catch the edge with the jaw of the caliper. The surface plate has none of those problems. This is perfectly vertical, and this distance from the bottom edge is perfect. The other great thing about surface plate work is that you can transfer these scribe lines around a part. That's something that's very difficult to do with most other methods. If you've done any amount of shop work, you've no doubt encountered this at some point. You've got a line scribed on a part or a dimension marked on a part, and either it's on the wrong side or you need it on multiple sides, and transferring that mark around corners accurately and to the far side of a part is actually pretty difficult to do. But on the surface plate, it's trivial. Because we have this absolute reference surface from the end of the part, we can orient this part any way we want, and we can transfer that line all the way around the part, and it's trivial to do, and it's completely accurate. And that kind of thing is really game-changing once you kind of understand all the applications of it. The fact that you have this absolute reference all the way around your part, and you can trust that your scribe lines are all going to line up on opposite sides of a part. So if you've got a tricky hole to drill and you need to drill it from both sides, let's say because it's too deep or it has some unusual geometry at one end, you can mark that hole position on the opposite sides of your part on the surface plate, and you can trust that they are going to line up in the middle. That's the kind of thing that is very difficult to do any other way. Don't underestimate how powerful that ability is, especially in something like model engineering, where you're frequently working with castings or large irregularly shaped objects. If you want to transfer, for example, the position of this water inlet to the other side for the same fitting on the other side, on a surface plate, this is trivial. You literally just put the boiler on your surface plate, find the height of one fitting, run around to the other side and scribe the other one, or if the fittings aren't there yet, decide where you want them and scribe the height. You can scribe a line all the way around this thing if you want and have a perfect center line reference, which on a giant sheet metal cylinder is a pretty difficult thing to do normally, but on the surface plate, it's literally trivial. Of course, if you're paying attention, then you might have noticed all of these things that we're doing all reference a particular surface or edge on the part. So these lines that I've scribed on this bar are all relative to that bottom surface. That is your reference surface for the part, and that is very important in surface plate work. You cannot do anything on the surface plate until you have a reference surface or a reference edge. So that surface has to be machined and square to your part, or in the case of this sheet metal, that bottom edge has to be machined or otherwise accurately produced. In this case, this happens to be a factory shear cut, and that's generally accurate enough, assuming you're going to process the other edges anyway, but you have to have some common reference edge for all of the features on the part. Because of course, if this edge wasn't perfectly square, then, let's say this thing is crooked, I'll exaggerate for effect here, then when I rotate that part around, we're not referencing the same place on the other side. We're at a different angle now, and the height on the ends is going to be different if that bottom surface isn't square. So the accuracy of your work is somewhat dependent on the accuracy of the surface being referenced on the surface plate. Those references can also compound when you start using reference or fixturing blocks for your part. So for example, a V-block on a surface plate is very useful when working on round stock. If you're marking dimensions or features on the edges or the ends of anything round, you can set it in a V-block and you can reference the top surface. And again, using the superpower of the surface plate, we can swing this part around, we can move it anywhere and mark features all the way around this part, and they're all going to be accurate relative to each other as long as we're always working relative to this V-block. But this means that the bottom of our V-block has to be accurately ground, and the surface sitting in the V-block on the part has to be a reasonable reference. This happens to be a factory cold-rolled surface, which is okay. Ideally, this would be a machined part sitting in that V-block, so it would be as accurate and as repeatable as possible. But for the purposes of this demonstration, it'll be good enough. So the next key skill in surface plate work then is zeroing. So I'll draw a feature on the end of this bar. In fact, I'll mark the center line at the end of this bar. Maybe you want to drill it out on a drill press or something. You just want to accurately find the center. So I'll start by finding the top of my bar. And finding the top of something is something you do very, very frequently on the surface plate. And this is rather like measuring something with feeler gauges. You're kind of going for that light drag feel. You don't want to be pushing down on it too hard, because of course if you push down hard enough on this, you can deflect it, and that's going to mess up your measurements. And it's not very good for the height gauge. So you want to kind of have a light drag and not be pushing down on the part, and also not be floating above it, of course. And also, if you push down on it too hard, you can move the part. You might tip the part up even a tiny amount without realizing it if you're really pushing down hard on it. So you're kind of going for a light drag there. A good trick to know if you're too far down, or if you're pushing down on it too hard, is to pull the height gauge away off the part and then slide it back in, and it shouldn't catch the edge of the part. If it does, then it was pushing down on it, and when you pulled off the part, a little bit of deflection was released, and then when you go back in, it's going to hit the edge of the part. So if you can pull it off and on like that without snagging, then you're in a good spot. Now, whatever this reading is on my height gauge is the height of that top surface of that part. So if I want to mark the center line of this cylinder, then I just need to subtract the radius of the cylinder, which of course I can measure with a micrometer. This is where a digital height gauge is a nice thing to have, because you can literally just push the 0 button at this point and move down by the delta that you need. But since this is old school, or I guess medium school, because it's a fancy modern height gauge, I didn't have to use gauge blocks to set the pointer, but it doesn't have batteries. So here we go. So moving close to the dimension that I'm aiming for now, there is a fine adjust on height gauges that you can engage once you're close, if it helps. I mean, once you have a little bit of skill with moving it, you don't necessarily need this, but what you can do is tighten this little guy right here, and then this little knob right here will allow you to do very fine adjustment to get down to exactly the reading that you're supposed to have. There we go, and of course you want to get down low. Make sure you're not getting any parallax on the needle. Boy, I'm really making digital height gauges sound like a good idea, aren't I? You can zero them. They don't have parallax issues. You don't have to do all this math. Yeah, anyway, I hate batteries, okay? I really, really hate batteries. All right, moving right along. Now that I've got the height established for my center line of the cylinder, I can scribe that. So, and now, of course, I can just rotate the cylinder, again, assuming this is a reasonably round surface, ideally a machined one, but again, for this demonstration, it's close enough. But being a valid circular reference, I can rotate the part and scribe another line. Do it a couple times. The angle doesn't matter a whole lot for a center scribe. But there you go. So there's the center of that cylinder. You really only have to do it twice, of course, on a surface plate. It's not like center finders where you have to do it a bunch of times and find the average, because of course this is accurate. Each of these lines is the perfect center line, so 2 of them is sufficient to find the exact center. A minute ago I talked about how surface plate layout is basically the same as bench layout, but it's all vertical. So that means that in order to get, say, an intersection point of 2 lines on a surface for perhaps like where you want to machine to, or where you want a hole, you want intersecting lines, that means you're going to need to be able to rotate your part 90 degrees and scribe lines on the other axis of the part. So I can set my part up like this, scribe an appropriate height, and there's my center intersection point for, let's say, a hole that I need to put in there. Now I can center punch that and move on from there, just like you would with bench layout. Of course, in order to do this, then you need a 90-degree reference edge on your part. You need 2 reference edges that are 90 degrees to each other, and you need to be careful when doing your layout that you're always using those same 2 edges. Even if all the edges of your part are machined, you generally want to do all of your layout from the same 2 edges. So even if this edge was also square, you want to avoid flipping it up like this and then taking a measurement from that end to find a feature from here. This is going to tend to introduce accumulated error, or what machinists like to call tolerance stacking, because even if this edge is machined, you're relying on the length of your part being absolutely perfect and not introducing any error. If you measure in from both ends for different features, there's going to be error in the middle between those features, depending on how accurate the overall length of the part is. So it's not generally a good idea to do that. You want to do all of your measuring from the same origin corner, if you like, of the part. So call this your 0, 0, and measure everything in from this edge and up from this edge. The other area where the surface plate has a real superpower in terms of layout is with castings. And this is, in fact, an area where bench layout really can't do this job. Proper layout of castings really requires a surface plate. Because of how irregular everything is, that simple ability that I talked about to transfer dimensions and positions around the part becomes the entire ball game. So laying out a casting is a difficult dance, because you've got all of these features that are rough cast. So there's sand cores that have been put in here for, in this case, a piston bore and a valve bore. And you have to get the center lines of those holes the exact correct distance from each other, for example. And you cannot use these existing holes as any kind of reference. They are completely arbitrary. They are literally blobs of sand that have been stuck in there. There's nothing less accurate than that. These holes only exist to help you get your tooling in there to get started, so you can get a boring bar in there or what have you, and so you're not paying for cast iron that you don't need. The whole point of castings is that they are a first order approximation of the part, and approximation is the operative word there. Nothing on this object can be trusted. Everything is a very approximate surface. However, all the features that you're going to put in this object have to be exactly the correct distance apart from each other in every dimension. So there's going to be a bore here, and there's going to be some feature on the end here, and there's going to be something over on the side bosses here, and all those features relative to each other have to be the exact perfect distances apart. And everything has to be done such that, for example, when you machine this bore to final dimension, it doesn't get too close to one edge. It has to end up centered on approximately on these cast edges here. So you have to have this feature and this feature perfectly aligned, this feature perfectly centered in the bore, and nicely centered this way, so that when all of the features relative to each other are done, everything looks nice because all the three-dimensional features are kind of centered within the material available, if that makes sense. So that's the art of machining castings. And layout is an enormous help here, because what layout allows you to do is essentially trial fit your features. So you can come up with a position, let's say you think where the centers of these two drain valves should be, and where you think the center of these two bores should be. And in fact, laying out features within a casting is one of the primary ways that surface plate work was used back in the day, because of course machining castings has always been one of the primary things that machine shop manufacturing is for. You know, in a hobby shop we work a lot with bar stock, but of course in the real world of manufacturing everything starts with castings, because it's a lot more efficient on materials and opens up a lot more design possibilities. I mean, you couldn't make a shape this intricate without a casting. I mean, you could, but it would be an enormous amount of work to create all these curves and so on, and it would be silly to do that. So casting is an enormously powerful tool, but machining castings accurately is a difficult job. However, the surface plate makes it an order of magnitude easier. The process is the same as with the bar stock. You start by creating a reference surface. So I would machine probably this face here flat, and that would allow me to set it down on my surface and accurately measure heights from that surface, and also accurately transfer marks all around this part. But then the question becomes, how do I lay out features on the top here, right? Because of course there's nothing I can use here as a reference. There's nothing I could machine to give myself that 90-degree reference that I talked about. But that's where your blocks and squares come in. So you can bring in a block like this, and you can reference that machined face on the back like so, and you can trust that the orientation will be good this way. As for this way, you can kind of pick an orientation that is going to be accurate enough for your layout, because again, you can think of the casting layout as a trial run of the machining that you're about to do. It's an experiment to see where things need to go, because generally the actual positions of these features relative to the casting are approximate, because of course there's nothing accurate about these surfaces. So it doesn't have to be that accurate in terms of distance on center line or things of that nature, as long as you're consistent about it, and as long as the features end up correctly spaced relative to each other within the casting, then all you're dealing with is aesthetics. You want this bore to look nicely centered in the casting. And of course, make sure that you're not going to break through any surfaces when you machine, but generally there's plenty of material in there. It's just a case of making things look nice when you're done. So for that reason, you can simply use packing under here to keep this surface oriented this way in a reasonable sort of fashion, as long as you're consistent about it. So, you know, super glue a packing block to this position here, let's say, and always use this surface of the casting for your reference. Because if you've got some sort of packing block that isn't going to move super glued on there, and then the rest of the casting is kind of sitting on these bosses in some arbitrary way, as long as it's consistent from measurement to measurement, it'll still do the job that you need. And as you're doing your layout, you want, of course, get these center lines of these bores reasonably centered within the casting. You can do the layout, and if it comes out a little crooked, like the center line of this bore is a little bit, you know, too low, for example, means your packing block is a little bit too high, so you can reduce the size of it and try again. And that's the great thing about laying out castings on the surface plate, is that you can just try again if it doesn't work out. You only get to machine it once, but you can throw layout dye on there and scribe it as much as you like. I would go so far as to say, in a model engineering shop, if you're going to be working with castings, this is a Stewart triple expansion engine casting, I believe, surface plate work is arguably essential. I mean, most of what I've shown you so far can be done just as well using edge finding and a digital readout on a milling machine, and we'll talk about that in a second. But with casting work, really, it's hard to beat the surface plate. The surface plate is still the best way, in my humble opinion, to lay out castings. Okay, but if surface plates are so great, why don't we use them anymore? Well, I mean, we do still. They still have many applications, but they aren't the go-to or the daily use kind of thing that they used to be. And the main reason for that, of course, is digital readouts. Well, I mean, it's CNC, but even talking pre-CNC here, digital readouts largely do most of the same jobs as the surface plate does. And frankly, in many cases with more accuracy, at least when we're talking about bar stock. So when you find the edge of something with your edge finder and then you zero your DRO, or if you find two edges and then center that axis of your DRO, you're doing the same thing that the surface plate is doing. The edge finder is essentially acting as your reference surface sitting on the surface plate, and then when you zero your DRO, it's creating a virtual surface plate that's sitting on that surface of your part. So then when you translate on X from there, let's say you're moving in X as though the part was sitting like up against a 1, 2, 3 block on your surface plate. So same job, it's just being done kind of virtually. Okay, given all that then, if you have a digital readout on your milling machine, why would you care about the surface plate? Why get one? Why use one? Well, in addition to what I said at the top about learning traditional methods being valuable in ways that you may not appreciate, the surface plate does have a couple of abilities that digital readouts are not good at, one of which is, as I said, laying out castings. Edge finders don't work on castings, right? The surface is too rough. Edge finders rely on a reasonably smooth surface in order for their little dealio to kick over, or if you're using something like a Heimer or a touch probe, they still, depending on exactly where you touch on the surface, is going to greatly influence the reading because castings are very, very rough. And that reading isn't repeatable. If you come back in and edge find again, you're going to get a different reading. Whereas on the surface plate, because it's averaging the entire surface of that rough casting, it's going to give you a consistent and repeatable number for where 0 is on that surface. So you can think of the surface plate as an infinitely wide edge finder. I say averaging, but I mean, if you want to be technical about it, you're finding the high spots of all of the surface, right? Which is a good approximation for the overall surface. The other reason you see me do a lot of layout, even though I have a digital readout, is that it's an excellent sanity check. As we all know, mistakes in machining are very expensive. A single wrong cut can scrap a part and can cost you hours, days, even weeks of work. So any tool in your toolbox that can help you prevent mistakes is infinitely valuable in my opinion. And layout is a great sanity check on every single cut that you're going to do on the milling machine. If you think you're getting close to your dimension on a digital readout, you're just going to keep cutting until that number says something, and then when you're done, you measure it, and you might find out you're 100th thou off because you made an error in your math, or you didn't read your edge finder properly, or you forgot to apply the radius offset for your edge finder. There's a million sources of error, right, that can scrap your part. And if you're just assuming you did everything right and reading the numbers on the DRO, sometimes it's not going to go right and you're going to scrap a part. However, if you've got a layout line on there, and that layout line has been determined with a completely different method, then that's an excellent sanity check. It's triangulating the correct value for that edge or that surface that you're making with different methods. It's like in science how we always want sources of evidence from different fields to converge on the truth. It's the same thing. So if you think you're close to your dimension and you see that your layout line is not close to where your cutter is, or if you're approaching your layout line sooner than you think you should, you can stop and check. You can start taking measurements. Maybe you did the surface plate wrong, or maybe this is wrong, or maybe you did your edge finding wrong, but you can stop and check everything and figure out what's going wrong before you make that last cut and before you scrap your part. The other place that traditional layout and surface plate work are still great is for rough cutting. Especially in a hobby shop, this is really important. The machine tools are small, they're not that rigid, and they're slow, and so you want to spend as little time on the machine tools as possible. I know they're fun, and that's why we're all here, but if I had to remove this whole section of material, let's say this was a thick bar, not a piece of sheet metal, I wouldn't want to do that on my milling machine. That would take an hour. But I can rough cut that out on the bandsaw in 30 seconds and then do a couple of finishing cuts on my milling machine and have this surface perfectly dimensioned in 10 minutes instead of an hour. So rough cutting with the bandsaw and other tools is really important in a hobby shop, and layout lets you do that. I can lay this surface out on the surface plate and then bandsaw cut just inside that line, and I know that I've got just one finishing cut left now to do to get that surface down to dimension. The DRO, of course, on my milling machine is no help here because I'm not doing this entire cut on the milling machine. I need to do it on the bandsaw, or I might be using the drill press to approximate a hole position, or I might be using the belt sander to get a piece of, the edge of this sheet metal close to my line. There's lots of, or the die filer, there's lots of other tools that you might use to approximate the surface before you go to the machine tools. The surface plate is going to be enormously valuable in all these scenarios for getting accurate layout lines because, again, remember, this line is a lot more accurate than if I had done it with the crooked scriber method, and the more accurate this line is, the fewer finishing cuts you'll need to do to get to your accurate dimension, and thus the less time you'll spend futzing around with the milling machine to get that surface perfect. And the surface plate is much quicker and much more accurate than any form of bench layout. I mean, you could draw this line just by measuring from the edge and putting a ruler on there and connecting it with a scriber. But no matter how carefully you do that, it's never going to be as accurate as the surface plate. And the surface plate is much faster. Rather than all that fiddly measuring and staring at the tiny marks on your scale, you literally just go whoop, whoosh, on your surface plate and you're done. That line is going to be perfect. Surface plate doesn't entirely replace bench layout, of course. There's some things you can't do. You're still going to need to center punch hole centers, and you're still going to need your dividers for laying out curves and circles and so on. So it's a supplement to bench layout, but anything that you can do on the surface plate, you should, basically. It will be more accurate, faster, and more fun, honestly. There are a few things in the hobby shop that are as satisfying as a beautifully laid out part done on the surface plate. It does such a nice job, and the process of scribing with that height gauge is very satisfying, and it's very enjoyable and makes you kind of feel connected to our very smart ancestors who invented all this stuff. Well, I hope something in here was useful. I hope it answered your questions about surface plates. Thank you so much for watching. Thanks to my patrons for making all of this content happen every single time, and I will see you next time.